So in this tutorial video, we will do some more problems. Uh, First, let me define something. Uh, Definition: a variety. Here we will always assume that irreducible. A variety y is normal at a point uh, p inside y if uh, the local ring at the point p is integrally closed. And y is normal if it is normal at every point. Okay, now I will do a problem from Hartshorne. I will do it as a proposition. Now, if y is an affine variety, then y is normal if and only if the affine coordinate ring ay is integrally closed. Okay, and the second part is let y be an affine variety, then there exists a normal variety y tilde and a morphism pi from y tilde to y satisfying the following universal property. Universal property. What is the universal property? For any normal variety z and any dominant morphism, say phi from this z to y, the dominant morphism means this closure of the image, this is actually equals to y. Okay, there exists a unique morphism theta, say from z to y tilde, such that this phi is equals to pi composition theta. It means this diagram, that suppose I have a map morphism from z to y, this is phi, this is a dominant morphism and z is a normal variety, then there exists a and we already have this y tilde to y, we have a map pi such that this phi factors to this pi, means there exists a unique map theta. from Z to Y delta such that this diagram commutes. Okay. So then this Y is called the normalization, the normalization of Y. Okay. So this is the statement of this proposition. Now first we will prove the first part. It says that if Y is an affine variety, then Y is normal if and only if the coordinate ring AY is integrally closed. Now this is actually very easy. Okay, prove this number 1 follows from the fact that integral integral closure, yes, integral closure is a local property, is a local property. See Atia MacDonald commutative algebra book, Atia MacDonald, and the fact that this local ring at point P, this is actually isomorphic to this coordinate ring localized at this maximum ideal MP, this corresponding to the point P. So from this it will follow, means that the first part means if Y is an affine variety, then Y is normal if and only if AY is integrally closed. So this will follow from this observations, means that integral closure is a local property and this local ring is isomorphic to this AY MP. Okay. Now number 2. For that, first I need to state a result from commutative algebra. Okay, a result from commutative algebra. Yeah, this is called the finiteness, finiteness of integral closure. Okay, it states that suppose A, let A an integral domain which is also a finitely generated K algebra, and suppose this a K is the field of fraction of this integral domain A, and suppose L is a finite algebraic extension of K, capital K, finite algebraic extension, and A prime is the integral closure of A in L. Then A prime is a finitely generated A module as well as finitely generated K algebra, small k, K algebra. So this is the result that we need for this second part of this proposition. So it states that uh, means if A is a integral domain which is a finitely generated K algebra, and suppose that capital K is the field of fraction of A, and if we have a finite algebraic extension L over this capital K, and if A prime is the integral closure of A inside L, then A prime is a finitely generated A module, and also it is a finitely generated K algebra. So okay, so now we come back to our the proposition, the second part of the proposition. Now here we assume that Y is an affine variety, right? So now we know that this field of fraction of this AY, this is actually the field of rational functions on Y, this KY. We have already seen it. Okay, now consider the integral closure of AY in this KY, K of Y, say A prime. Okay, then from the previous result, the result I've just stated, this A prime is a finitely generated integral domain over K. Okay, this follows from the previous result. Okay, and this A prime, this which is also integrally closed, Why? Because A prime is the integral closure of A of Y inside K of Y. So of course A prime will be integrally closed, right? Because integral closure is integrally closed. Okay, then there exists an affine variety Y tilde such that this coordinate ring of Y tilde, this is isomorphic to A prime, isomorphism as K algebra isomorphism. Why? This follows from the follows from the equivalence of categories. Equivalence of categories between the category of affine varieties over say field field K. Of course, algebraically closed, we will always assume that field is algebraically closed, and the category of finitely generated integral domains over field K. Okay. So yeah, from this it follows that means if this A prime is a finitely generated integral domain over K, which is also integrally closed, Now because it is a finitely generated integral domain over K, so from this equivalence of categories we can say that there exists an affine variety y tilde such that A of this coordinate ring of y tilde, this is isomorphic to A prime. So there exists such a y tilde, and this y tilde which okay. Okay, so this y tilde is also integrally closed, right? Because it's a affine variety. So means from the uh, previous part, in the first part of this proposition, it follows that so this y tilde will be also normal. Okay. Okay, fine. So okay, now now we have an injective K algebra map, K algebra homomorphism from this ay to ay tilde. So ay tilde is like integral closure of ay, right? So this will imply this will give us a map y tilde to y theta, say, and because this is injective, so this will be a dominant morphism. Dominant morphism. Okay. So now we have a normal variety y tilde and we have a dominant morphism theta from y tilde to y. Okay. Now we have to show the universal property. Now suppose this z is a normal variety, and suppose we have a dominant morphism z to y, say phi, a dominant morphism. Okay. Now this will imply that this ay to OZZ, this is phi star y, is injective. Okay. Now this will be, I will leave this as an exercise. You can easily verify this thing. Now reduce to the case when z is an affine variety. Okay. For that, consider an affine cover. Affine cover. Consider an affine cover. Now after this reduction, now we can assume that z is affine. Z is an affine variety. Okay. Now this will say that this ay to this az, this is injective, right? Now ay this is inside its field of fraction k of y. Now this k of y, here to this k of z, we have a field extension. Okay. Now we have now this of course not just field extension, this will be a means finite algebraic extension. Now we consider this now A of z, this is integrally closed, this is integrally closed in this kz, and A of y tilde is integral closure of ay in ky, right. Now this will imply that A of y to means this A of y to A of z, this will factor through A of y tilde to this. So this will be the case, and okay, now this diagram will give us this diagram, means if I have z to y, if I have this morphism, this phi, and this y prime to y tilde to y, we have this morphism pi, then it factors through this morphism theta, and this is unique such that it commutes. So okay, so we are done. So now one example, every conic in P2 is normal. It follows from a Hartshorne exercise that a Hartshorne exercise, it follows that every conic in P2 is isomorphic to this P1. Now for P1, if we consider the local rings of P1, then we have to show that it is local ring at any point. We have to show that it is a regular local ring, which in turn means every regular local ring is a UFD, and every UFD is integrally closed. So from there it will follow that means every conic inside P2 is normal. Okay, let me stop here.